Alright, so we're going to do question 8 in workshop 1 for negotiation and market strategy. Alright, so in question 8, it's telling you that on a peaceful Sunday afternoon, Malcolm and Angus each simultaneously decide whether to go to Greystanes or Rooty Hill. Okay, so if both of them choose to go to Greystone, each of them is going to get 5. If both of them decide to go to Rooty Hill, Malcolm will get 1 and Angus is going to get 0. If Malcolm decides to go to Greystones and Angus decide to go to Rooty Hill, the payoffs are going to be 3 and 2. If Malcolm decides to go Rooty Hill while Angus decides to go to Greystones, the payoff is going to be 0 and 1. Okay, so they're asking you whether each of the players have a dominant strategy, and if so, what is going to be the dominant strategy? Equilibrium, and whether this is the prisoner's dilemma game. Okay, so again, first thing we want to do is to write out the payoff matrix. Okay, so the normal form of the game. So we have 2 players, Malcolm, okay, and Angus. Alright, so again, if you want to put Malcolm over here, Angus over here, it doesn't really matter. Okay, it's just totally exactly the same thing, and you get the same result. Alright, so they can have 2 options, either go to Greystone, which is Chi, or to go to Rooty Hill, which is RH. Okay, so it's very similar for Angus. He can either go to Greystones or go to Rooty Hill, so the Chi or RH. Okay, so the payoffs, we just have to fill out the table over here. Now the question telling you if both of them decide to go to Greystones, each of them is going to get 5, so it's going to be 5 and 5. Now if both of them decide to go to Rooty Hill, Malcolm is going to get 1 and Angus is going to get 0. Okay, now seeing I put Angus over here as the first player, the first payoff is going to be for Angus. Okay, so therefore the first payoff is 0 for Angus and 1 for Malcolm. Now if Malcolm decides to go to Greystones, which is here, and Angus decided to go to Rooty Hill, which is here, the payoffs are going to be 3 to Malcolm and 2 to Angus. So I would like to write 2 first for Angus because that is the first payoff for the first player, and 3 for Malcolm. Okay, so remember, whatever you're writing here in the matrix, in the payoff, it has to be consistent, and you have to know what is the payoff for what player. Okay, so do not get yourself confused. Now the easiest way to always be consistent is that the one on the horizontal over here, okay, is always going to be the first player, and the first payoff or the first number in the payoff cell is going to be for the first player. Okay, so always using the same sort of method, okay, sort of writing, in order to make sure that you are consistent and you know what payoff is for what player. Okay, so if Angus decides to go to Greystone and Malcolm decided to go to Rooty Hill, which is the last one over here, the payoff is going to be 0 to Malcolm and 1 to Angus. Okay, so 1 to Angus and 0 to Malcolm. Okay, so we are done writing the game, the formal form of the game. Now we just have to find the strategy for each of the player and the equilibrium. Okay, so we are going to do exactly the same thing as what we have been doing. So we find the optimal strategy for Angus first. Okay, so again, we just be asking ourselves, if Malcolm decide to go to Greystone, okay, it's Chi, then what is going to be the optimal strategy for Angus? Okay, so optimal strategy for Angus is going to be, now if Malcolm decided to go to Greystone, that is going to be the first column over here that we are looking at. Now Angus, by going to Greystone as well, is going to get 5. by going to Root T Hill, he's going to get 2. So therefore, going to Greystone is going to be better. So I put 1 star here. Okay. So the optimal strategy for Angus is to go to Chi. Alright, now if Malcolm decides to go to Root T Hill, which is the second column over here that we're looking at. Now Angus, by going to Greystone, he's going to get 1. Going to Root T Hill, he's going to get 0. 1 is better than 0. So therefore, the optimal strategy for Angus again is to go to Greystone. Okay. So if you're looking at this, we can see that Greystone is going to be a dominant strategy for Angus, because he's going to go there anyway. Doesn't matter what Malcolm is going to do. Okay. Alright, so yes, Angus is basically having a dominant strategy. Okay, now how about Malcolm? Alright, so now if Angus decide to go to Greystone, what would Malcolm do? Okay, so we're basically looking at the first row over here of the matrix of the table. Okay, where Angus decided to go to Greystone. Now Malcolm, by going to the same place, is going to get 5. By going to Root T Hill, he's going to get 0. 5 is better than 0. So therefore, I put a star here to indicate that the optimal strategy for Malcolm in this case is to go to Chi. Okay. Alright, now if Angus decide to go to Root T Hill, what is going to be the optimal strategy for Malcolm? So we are looking at the second row of the table where Angus decided to go to Root T Hill. Now Malcolm can either go to Greystone or Root T Hill. Go to Greystone, he's going to get 3. Root T Hill, he's going to get 1. 3 is better than 1. So therefore, I put a star there to indicate that optimal strategy for Malcolm is to go to Greystone. Okay, so again, going to Greystone is going to be a dominant strategy for Malcolm as well. Because he's going to go there anyway, it doesn't matter what Angus is going to do. Okay, so yes, the answer to the question, does each player have a dominant strategy? Yes. Okay. Now, if so, what is the dominant strategy equilibrium? So as you can see, the equilibrium in this case here is for Angus and Malcolm to both go to Greystone. Okay, so the equilibrium is Chi and Chi, and this is a dominant strategy equilibrium because that is the equilibrium in which the two players are choosing the dominant strategy. Okay. Now it is a prisoner's dilemma. So again, in order for a game to be a prisoner's dilemma, it has to be the case that each of the player has a dominant strategy, which is yes. Okay, a unique dominant strategy equilibrium, which is yes in this case. Now the last condition is that the total surplus has to be not maximized. Okay, so in this case, as you can see, the total surplus in this case is 10. Okay, and each of the player is getting 5. Now if you compare to all other strategies, none of the strategies is going to give the player a payoff higher than 5. Okay, so if they go to this one, each of them is going to give the player a lower payoff than what they have already been doing in equilibrium. Okay, so this equilibrium turns out to be the optimal outcome for the two players because giving the two players a highest payoff, okay, among every other strategies. So therefore, we're saying that the equilibrium is okay, the optimal outcome. Alright, because the total surplus or the total payoffs for the two players. Okay, is maximized. Okay, so as you can see, there is no other strategy in which the player can earn higher than this equilibrium strategy. So therefore, we confirm that this is not the prisoner's dilemma, because the equilibrium is the optimal outcome. While in the prisoner dilemma, we require that the equilibrium is not the optimal outcome. Okay, so therefore, the game is not a prisoner dilemma game. Okay.